Hi everyone, welcome back to the channel. In this video, we are going to discuss about the our PNP and NPN transistor. If we are going to introduce the transistor is a electronic device and which can be used as a switch to control the current with a smaller one. For example, powering an LED and they can amplify small AC signal. We will focus on two main types of transistor, that is NPN transistor and another one call it as PNP transistor, and these both classified as bipolar junction transistor BJTs because they have two junctions. Let's first look at the NPN transistor, and if we consider this NPN transistor, there is a three type of material, that is one is N and another one is P and another one is N. There is a first junction between the P and N type of material. This is the first junction, and here second junction is also present. It is between the P and N type of material. This is the junction, giving its bipolar in nature. In NPN transistor, the emitter and the collector, this is the collector and this is the emitter, is made up of N type of semiconductors, and the base is made up of P type of semiconductor. And this NPN transistor can be visualized as a two diodes connected back to back, which will be like this. This diode's arrow indicate always pointing towards the N type of material. A typical diode has a two type of material, which is P type and the N type of material. And here anode is made up of P type of material and the cathode is made up of N type of material. The current flowing through the diodes in one direction, which is in the forward bias condition. When the anode is connected to the positive terminal of the battery and cathode is connected to the negative terminal of the battery, there is a resulting into the voltage drop across the diode about 0.6 to 0.7 volt in silicon diode. If the polarity of the silicon diode has reversed, that means the positive terminal is connected to the cathode and the negative terminal is connected to the anode. It enters into the reverse bias mode and is essentially off unless maximum reverse voltage is exceeded. Understanding forward and reverse bias is crucial for the transistor analysis because it determines the transistor operating region, that is active and cutoff and saturation. Now let us discuss on PNP transistor, which operates with the reversed polarity compared to the NPN transistor. Instead of NPN, it has PNP layers. In this PNP transistor, the base is made up of N type of material and while collector and the emitter is made up of P type of material. The equivalent circuit symbol of PNP transistor looks to be different. A small NPN and PNP transistor have specific physical appearance. For example, here we are going to consider the transistor part number 2N2222. For a 2N2222 NPN transistor, it is looks to be somewhat like this, and this is a emitter pin and This is the base pin and this is the collector pin. Emitter, base and the collector. Now let's learn how to draw the electrical symbol for NPN and PNP transistor, especially for circuit diagram. Starting with NPN transistor, first draw a circle and then the baseline. The emitter arrow is pointing away from the base. This arrow always represents the emitter pin, and this is the baseline and this is the collector line. For PNP transistor, the baseline is the same position, but this time the emitter arrow pointing towards the base junction, and this is the emitter terminal and this is the collector terminal. Okay, the particular symbol is like this. For PNP transistor, the baseline is in the same position. That is here, but this time the emitter arrow is pointing towards the center, and that is the collector terminal. Okay, this is the emitter terminal, this is the collector terminal, and this is the base terminal. And in PNP transistor, this emitter terminal often connected to the ground. For PNP transistor, the collector is usually connected to the ground terminal, and this emitter goes to the positive source. And in NPN transistor, the collector goes towards the positive source volt. For the base of an NPN transistor, typically connected to the positive voltage source, while PNP transistor is connected to the ground. It is crucial to include a resistor in series with the base terminal here to limit the base current. An excessive base current can damage the transistor by allowing a large collector current, leading to overheating. In NPN transistor, the current will flows into the base terminal of the transistor, whereas in a PNP transistor, the current flows out from the base terminal of the transistor. Remember that this is opposite to the direction of electron flow. The conventional current flow from higher to lower potential, where the electrons flow from low to high potential. Using conventional current simplifies analysis because the direction of the emitter arrow indicates the direction of emitter current. In NPN transistor, the collector current flows towards the transistor in this way, and emitter current flows away from the transistor in the direction of emitter arrow. For a PNP transistor, the current flows from positive potential to the ground. The emitter current flows in the direction of emitter arrow. The collector current flows away from the transistor, and the base current also flow away from the transistor. Thus, NPN and PNP transistor are opposite in terms of current flow direction at their terminals. The emitter arrow's direction always indicates the direction of emitter current, regardless of whether it is an NPN or PNP transistor. For the most part in our circuit analysis, we'll focus on NPN transistor. Now let's review some important formulas for transistor analysis. The first is collector current IC, which is collector current and which is equal to, that means IC is equal to beta times IB. Here IB is the base current of the transistor, and here beta, which is the current gain of the transistor. Beta is also often denoted as HFE, and we can find this value in transistor datasheet. It represents the current gain of the transistor. In second, the emitter current IE is equal to sum of IC and IB. By substituting IC with beta IB, we can express IE is equal to beta plus 1 times of IB. It is most important to understand these two fundamental equations and be able to drive the third if we need it. Here an example, consider an NPN transistor with the base current IB is equal to 50 microamps and the beta HFE is equal to 200. Let's calculate the collector current and the emitter current. By considering the formula, the collector current IC is equal to beta times IB. When we substitute the value, which is equal to 200 times of 50 microamps, which is equal to 10 milliamps. So that emitter current IE is equal to IB plus IC, which is equal to 50 microamps plus 10,000 microamps, which is equal to 10,050 microamps, or we can call it as 10.05 milliamps. Notice that the beta, which we can call it as HF, is larger, typically greater than 100. The emitter current IE is approximately equal to the collector current IC. For example, in our calculation, we can see here the collector current is 10 milliamps, and similarly the emitter current is 10.05 milliamps. There is no that much of difference in between IC and IE. It is approximately equal to each other. This approximation can simplify calculation in more complex transistor problems. Now let's look at typical NPN transistor circuit. NPN transistor circuit. We have a base terminal and the collector terminal and the emitter terminal. It is the base terminal, and this is the collector terminal, and this is the emitter terminal. Here we can consider the base resistance. We can call it as RB, and the collector resistance we can call it as RC, and the emitter resistance we can call it as RE. Another terminal of the resistor is connected to the ground. Here VE represent the potential difference at emitter terminal with respect to the ground, and here VCs represent the voltage across the collector terminal. The VB is the potential at the base terminal, and this VCE is the voltage difference between collector to emitter terminal, and which is equal to VC minus V, and which can be measured by connecting multimeter across the collector and the emitter terminal of the transistor. Here VBE is the voltage difference between base and the emitter terminal of the transistor, and which we can call it as VB minus VE. For most of NPN transistor, which is VBE is typically 0.6 volt to 0.7 volt, and the voltage VCB is the voltage difference between collector to the base terminal of the transistor. We can call VCB as VC minus VB. Here we can represent the collector supply as VCC. In this case we are considering plus 9 volt, and here VEE, which represent emitter supply, which in this example we are considering it as 0 volt. So we don't need to consider it for this specific circuit. Let's see how the transistor function as a switch. We have a 12 volt battery connected to the base terminal and the emitter terminal through switch S1 and base resistance RB. This is the base terminal of the transistor, and this is the collector, and this is the emitter terminal. This is the collector terminal, this is the base terminal, and this is the emitter terminal. This is NPN transistor. And similarly, there is a 12 volt battery which is connected to the collector terminal and the emitter terminal of the transistor through the collector resistor RC, and there was a LED into it, and the negative terminal is connected to the emitter terminal, and we can represent LED as a D1. This is also 12 volt. When the switch is open, there is no current flowing into the base terminal of the transistor. For transistor to turn on, we need at least 0.6 volt for silicon transistor, or it should be greater than that. Since there is no base current, the transistor is in off condition, and there is no current flow from collector to emitter. So LED will be in. So LED also in off condition. This is switch 1S. Let's close the switch. Now the current flowing from the positive terminal to the base terminal of the transistor, creating a base current IB. Once the base potential reaches 0.6 volt, the transistor turns on. This allows the current flow from collector to emitter terminal through the collector resistor RC and through the diode. Once current passing through the diode D1, the LED gets on. This demonstrates that how a small base current can control the large collector current, which is the key function of transistor switch. Let's analyze a circuit like this with some values. And here we are using NPN transistor. This is the base terminal, this is the collector terminal, and this is the emitter terminal. And let us consider the base current as RB, and we are considering it as 100 kilo, a large resistance to limit the base current, and the collector current RC, let us consider as 1 kilo to limit the current through the LED, typically around 20 to 30 milliamps. Let us consider this collector terminal to the 12 volt battery. A 1 kilo ohm resistor would allow a maximum 12 milliamps. As per Ohm's law, V divided by R is equal to 12 volt divided by 1000 ohm, which is equal to 0.012 amps. This is the maximum collector current, and we can call it as the saturation current. IC sat is approximately VCC divided by RC by ignoring the RE. For this problem, let us change the collector current RC to 220 ohm and set the transistor beta is equal to 100, and the transistor symbol we typically we will represent it as Q. We need to calculate the base current IB and the collector current IC and emitter current IE, and we need to calculate potential at C and B and the E and value of D. C, B and value of D, and here also base terminal connected to the 12 volt, and this is connected to the ground. Emitter is connected to the ground terminal. Okay, the positive terminal is connected to the resistor RB. This is the 12 volt. First set the ground potential to 0 volt, assuming that VBE is equal to 0.6 volt. The base current IB can be calculated by using Ohm's law. IB is equal to VA minus VB divided by RB, which is equal to 12 volt minus 0.6 volt divided by 100 kilo, okay, which is equal to 11.4 volt divided by 100 kilo ohm, which is equal to 0.114 milliamps. So that collector current IC can be calculated as IC is equal to beta times IB. So beta is equal to 100 into 0.114 milliamps, which is equal to 11.4 milliamp. Let's calculate the potential at the point D, which is the voltage drop across the resistance RC. So voltage at the point D can be calculated as IC into RC, which is equal to 0.0114 amps into 220 ohm, which we can consider as 2.508 volt. So that voltage at VD is equal to 12 volt minus IC into RC, which is equal to 12 volt minus 2.508, which is equal to 9.492 volt. To estimate the potential as point C, we need to know that typically the LED's forward voltage drop of approximately equal to 2 volt. It can be between 1.8 to 2.2 volt. So that VC is approximately equal to VD minus 2 volt, which is approximately equal to 9.492 volt minus 2 volt, which is equal to 7.492 volt. And collector to emitter voltage VCE can be given by VC minus VE, which is equal to 7.492 volt minus 0 volt, which is equal to 7.492 volt. For amplifier application, VCE often set to half of VCC for maximum signal swinging. There are three key operating regions of the transistor. One is cutoff region and another one is active region and another one is saturation region. For example, in cutoff region, the emitter potential VE is the higher than the base VB, meaning that the base to emitter junction, for example, if you see in the diode mode, it's a diode connected like this. This meaning that the base to emitter junction is in, because here is the higher potential and this is the lower. So it indicates that the base to emitter junction is reverse. The current opposes emitter error. And similarly, the collector potential also higher than the base, and the collector to base junction also in reverse bias condition. In the cutoff, the transistor is effectively off. The collector to emitter voltage V is approximately equal to VCC, and this collector current IC is close to 0 amps. Ideally, it is in nanoamps. Okay. In active region, the base potential VB is the greater than emitter VE. Okay, here which is higher and it is lower, and VBE approximately greater than or equal to 0.6 volt. The base emitter junction is in forward bias condition, and however the collector potential VC is still higher than the base terminal, so that collector base junction will be in the reverse bias condition. This reason is used for amplification purpose. And the third reason is saturation region. In this case, the base potential is still greater than emitter potential, which is VBE is greater than or equal to 0.6 volt, and is a higher and a lower the forward bias condition. But now the base potential is also higher than collector potential, which means VB is greater than VC, making the collector to base junction is forward bias as well. In cutoff region, the VCE is approximately equal to VCC. In active region, VCE is between 0 volt to VCC, and in this is for active region, and this in saturation region, VCE is close to 0 volt. And similarly in cutoff region, the IC is equal to 0 amps, and in active region, the IC is in between 0 to maximum saturation, that is IC sat. That means the IC sat is equal to, which is approximately equal to VCC divided by RC if there is no RE, or VCC minus V diode divided by RC if LED present. In active region, the collector current IC is equal to beta times IB, the base current. In saturation, increasing the base current IB will not significantly increases collector current IC. It is already at maximum state. You can determine the transistor operating region by measuring VC. If it is close to VCC, it is in cutoff region, and if it is close to 0 volt, it is in saturation. If it is somewhere between 0 to VCC, it can call it as active region. Also, if increasing the base current doesn't increase the IC, the transistor is likely saturated. For most ideal amplifier design, we need to aim for VCE is approximately equal to 0.5 times VCC, and IC is approximately equal to 0.5 times IC SAT, saturation current. This provides the maximum signal swing without clipping. I hope that this video is going to help us how to configure the transistor in different mode like cutoff and active and saturation region, and how to consider the collector resistor and the collector current, and the how to calculate the collector current and emitter current, and collector voltage and emitter voltage and the base voltage. If you have any doubt, please leave the comment in comment section below, and if you like this video, please like and subscribe our channel for more electronic tutorial. Let us see in the next video. Thank you for the watching.